Hi, I'm Kyle, a PhD student at Stanford University in the Aeronautics and Astronautics Department, and I've been working with Michael Kokendorfer on the use of neural networks in aircraft guidance and control systems. In this video, I'll present the slides that I gave during my PhD defense last week. So automation is used in many applications today, such as traffic lights, thermostats, and assembly robots. These systems are encoded with rules that lead to good behavior, such as a thermostat that turns on the air conditioning when the temperature rises above 80 degrees. So for these systems, it is possible to manually specify the action to take in all possible states of the system. So this is the classic approach to software engineering, and it's the kind of approach that led to the development of the Traffic Collision Avoidance System TCAS, which is a rules-based collision avoidance system that has been used on commercial aircraft around the world for many years and helps to keep us all safe when we're flying. And so this logic has these rules that tell the pilots in different situations whether they should climb or descend in order to avoid a near mid-air collision with another aircraft. However, there are a few limitations of this kind of approach. First, fixing issues can be complex. Changing the logic in one part of the code could have inadvertent side effects in other parts and could actually create new bugs in the system as a whole. It can be difficult to tune this logic as well for different airspaces or aircraft. As a result, you might have to start over from scratch trying to define this logic manually, and so it can be difficult to try to create different types and versions of this system. Autonomous systems, on the other hand, are systems in which defining the best action for all states of the system is very difficult, either because there's so much information that you're receiving, such as with autonomous vehicles, which have sensors for cameras, LiDAR, and radar, or because you don't know what the best action to take is, such as if you're playing a really complicated game like Go. So for these systems, we need to use optimization to learn what the best action is for all possible states. There are a lot of ways to create these kinds of autonomous systems, but the method that I'll be focusing on today is the Markov decision process framework, which has 4 key components that I'll describe now. So first, you need to define the states of the system. This is a way to mathematically describe the scenario that you're in. So for that collision avoidance problem, which is going to be a theme throughout this presentation, you need to have a way to define the position and velocities of the intruder aircraft you want to avoid with respect to the ownership aircraft, which is the one that we're controlling. So next, you need to define the actions that you can take. In this case, for the collision avoidance problem, this would be climbing or descending advisories that can be given to a pilot in order to try to avoid a near mid-air collision. Next, you need to define the state dynamics, which is a mathematical model for how the state variables are going to change in response to the actions that you take. And finally, you define some rewards, which is a way to encourage good behavior or discourage bad behavior. So for a collision avoidance problem, you might have a very strong penalty given for a mid-air collision, or some smaller penalties for giving climbing or descending advisories to a pilot. The idea is that you only want the system to give these advisories when it's important and necessary in order to avoid that near mid-air collision. The key idea is that defining these 4 components is a lot easier than trying to define the correct action to take in on all possible states of the system. And so we can use dynamic programming to compute a score for every state in action pair, such that taking the best scoring action in each state is the one that's going to accumulate the most reward over time. So this is the kind of approach that was used for the Airborne Collision Avoidance System X, or ACAS X, which uses this robust dynamic programming to create this advisory score table and became an international standard in 2018. So the idea is that you would use your sensor information to determine what state you're in, and then look up the scores of the different advisories to determine which advisory is best to give at that time. So this has some great improvements. One is that the advisory scores are easily tuned. It's just a matter of changing that reward function and rerunning the optimization again, such that you get a brand new score table out where everything is changed in response to the changes in the reward function. It's also possible to use this same framework to produce systems for different types of aircraft or different airspaces just by making changes to the way you define the states or your system dynamic model or the actions that you can give. So we can use the same framework and create a whole family of collision avoidance systems. However, there are some limitations. One is that the score table can be very large. We're enumerating values for all possible states of the system and all actions of the system, And so for some types of problems, this can be really large. And if you want to deploy this on real hardware with limited memory, it could be intractable to put it on board the real aircraft. One method to overcome this limitation is to use a parametric function approximation. The idea is that instead of storing all of these score values explicitly, we want to try to learn some function that best represents these values, so that we only need to store the parameters of the function rather than all of the score values themselves. So if there are fewer parameters than there are points, then we're going to have a savings in memory. So there's a lot of functions that we could use to try to represent this data. One type of function that has become really popular in literature is the neural network. And I'll explain how this works in a few more slides. But actually, the neural network has been employed in all of the autonomous systems applications that I mentioned earlier in the talk, at the very least for research purposes. Now, the limitation with neural networks is that they can be challenging to verify. So if we want to employ these neural networks in safety-critical aircraft systems, in which they're the last defense before catastrophe, we really need to be sure that these neural networks are going to act correctly and act safely. So this leads me to my contributions of my thesis. So first, I will discuss some neural network compression of score table policies to show that we can get really efficient representations of these optimized policies. I'll then describe two methods for neural network verification. The first method is to use the system dynamics to create safety properties that we can verify with neural network verification tools. And the second method is to use reachability analysis to determine if the neural network controller can ever reach unsafe states. So due to limited time in my defense, I'm only going to be talking about the reachability analysis, but I will give a little bit of the takeaways from the dynamics-informed safety properties methods. And then finally, I'll discuss validation of neural network controllers, which is especially important for image-based neural networks where these previous verification methods are not tractable. So first, let's talk about my neural network compression work of score table policy. So for this work, I studied the ACAS Xu system, or an early prototype of that system, which is a variant of that ACAS X system I mentioned earlier that's designed for unmanned aircraft and gives horizontal turning advisories rather than vertical climb or descend advisories to avoid an intruder aircraft. But it still uses that same Markov decision process framework. So we first need to define the states. In this case, there are 5 state variables to describe the horizontal geometry, and an additional variable tau, which defines the time until loss of vertical separation. So this acts as a countdown until the time we need to be separated horizontally in order to avoid a near-midair collision. And the 7th state variable is the previous advisory. So this allows the system to know what it alerted at the previous time step so that it can try to maintain a consistent advising behavior to the pilot. So next we have some actions. In this case, we have clear of conflict, which is essentially no advisory, allowing the pilot to maneuver the aircraft as they see fit. And then 4 different turning advisories of different strengths and different directions. So weak left and strong left, and weak right and strong right. So we then define the system dynamics and a reward model and end up with this optimized score table, this Q table, which defines scores for all state and action combinations. So in this system, there are 120 million different states that represents different discrete values of this different 7 state variables. And so in total, this represents 2.4 gigabytes in floating point precision. So this table gets used to create a policy pi, which is the best scoring advisory for every state of the system. So we'll be using these plots throughout this talk. But the idea is that the ownership is at the origin 0, 0 and heading in the positive x direction. The intruder is heading in the direction shown by the aircraft in the upper right corner, and we're plotting the advisory that the system would give if the aircraft were at that location. So if they're far away from the intruder, or if the intruder aircraft is not on a collision course with the ownership, we would issue a clear of conflict or give no advisory. And if their intruder aircraft is to our left, we'd give a right turn advisory, and if they're to our right, we'd give a left turn. And if they're closer to us, we might give a stronger advisory because it's more imperative that the ownership begin turning quickly to avoid a near-midair collision. So storing 2.4 gigabytes of memory can be asking a lot for avionics systems, especially for certified legacy avionics systems. So we want to find a way to compress that representation into a smaller functional representation. So in this case, we're using a neural network, which is a function that takes in the values of the state variables and outputs estimates of the score values. The idea is that only the function parameters need to be stored in memory. So this will greatly reduce the representation size if we have fewer parameters than we have values in the table. So now I'll describe a little more detail about how neural networks work. And specifically, I'll be talking about feed-forward fully connected neural networks. So they're composed of a number of layers. So there's the input layer, which is the values given to the neural network. There's some number of hidden layers, and then an output layer, which is the output of the neural network. So these hidden layers are created as weighted sums of the previous layer along with a bias term. And then you pass those through a nonlinear activation function. In this case, I'm using ReLU activations, which is max of 0 or the input to the ReLU activation. And then this process is repeated to form the next hidden layer until finally you compute the output layer as a sum of or a weighted sum of the last hidden layer. So we want to optimize these weights and these bias terms in order to create accurate estimates of the score values of the table. So this process is known as supervised learning. So first we would initialize these weights to some random values. We evaluate some sample of the data and then compute a loss term. So we're comparing the actual score table values to the neural network's outputs. And this loss function is a measure of how accurate our predictions are. And we would then use this gradient descent method in order to update the parameters of the neural network to try to minimize that loss term, and then repeat this process with new batches of the data and do this until that loss function stops decreasing. So choosing a loss function is really important when trying to optimize the parameters of a neural network. In this case, we actually have two objectives that we want to optimize for. We want to predict the policy pi as accurately as possible, which would mean that the system is giving the same advisories as the original score table. But we also want to predict the score values themselves as accurately as possible. This is important for a couple of reasons. If we're not sure about the state that we're in, we might have a distribution over states. And so to compute the best advisory given that distribution, we need to compute a weighted sum of the score values before taking the argmax to determine the best scoring action with respect to that distribution. It's also important if we have multiple intruder aircraft, we might need to do something known as utility fusion in order to determine the best action to take given some number of intruder aircraft. So to compute accurate approximations of the Q values, this is a regression problem, and we would typically use something like mean squared error loss. However, if we're trying to maximize both objectives, neither loss function works very well. So categorical cross entropy is not going to predict the scores accurately. It's only going to give us a probability of an advisory being given by the system, and it has no notion of the score values. Mean squared error might seem like it would work well, but actually it frequently changes the best scoring advisory. So this happens actually a lot in the table, as was found when the scores between the best two advisories are really similar. So mean squared error might make errors in the direction that could change the order of the advisories. And as a result, the system is going to be giving different advisories than the original system, and the behavior is going to be different, even though the values of the scores themselves are still decent approximations. So we created an asymmetric loss function so that we can try to approximate both the policy and the score table advisories as well as possible. The idea is that we give extra loss for errors that could change the best scoring advisory. So we give extra loss if we undervalue the optimal advisory or if we overvalue any of the other advisories. So in this way, we encourage that there should maintain that gap between the best scoring advisory and the other advisories. And if anything, that gap will grow. So this is still a quadratic loss function, and the loss is hopefully, and the network error is hopefully driven towards 0. But if the network does make errors, it's going to make them in the direction that maintains the order of that best scoring advisory. So we tried this regression for both the nominal mean squared error loss function as well as the asymmetric mean squared error loss function. what we're showing here on the bottom right is the confusion matrices. So ideally, we would see 100% agreement along this main diagonal, where which would mean that the score table and neural network advisories give the same. The score table and neural network give the same advisories in all states of the system. But when we use mean squared error, we see there's a lot of off-diagonal terms where the system might be giving a different advisory up to 25% of the time. But when we use that asymmetric mean squared error loss function, we get a much better match between the score table and the neural network. And so this indicates that this asymmetric loss function is very important in trying to maintain that same policy. So we trained a neural network that had 6 hidden layers and 600,000 parameters, which is a representation size of 2.4 megabytes. And what I'm showing here is some plots comparing the neural network representation to the policy of the original score table. So the score table is jagged due to this nearest neighbor interpolation that they use. But for the neural network, it's just a function, and we can pass in any state variables or values of the state variables through the function in order to compute the policy the neural network would give. So in general, this neural network results in a smoother approximation of the table, where most of the general shapes and regions are preserved. However, there are some differences in the two policies. There are some strong left and strong right regions out here on the neural network, which leads to the question of, are these differences going to compromise safety or degrade performance, which I'll talk a little bit about later. But in general, just looking at the policies created by the neural network compared to the table, it seems like a decent approximation and is a pretty smooth approximation to the original table. So we compare the neural network compression method to other types of compression methods. So one is to use the decision tree, which is a popular machine learning algorithm, and also origami compression, which was developed specifically for collision avoidance systems, and it seeks to remove redundancy in the table when possible. And so what I'm plotting here is the root mean squared error of the scores on the left and the percent error in policy on the right. So ideally, we would like both of these numbers to be minimized. And on the x-axis, we're plotting the size of the representation. So for the decision tree or origami compression methods to have that same level of accuracy as the table, you would have to have size representations of hundreds of megabytes, whereas the neural network is able to achieve accurate representations in both the scores and the policy for only a 2.4 megabyte size. So it's a much more efficient and effective method of compressing the score table values. However, one limitation of this approach is that there is an increase in the runtime when using the neural network because you have to do all of this computation as opposed to just looking up some values in a table. So we overcame this limitation by splitting up the table into a bunch of subtables. So we did this by looking at the different combinations of the tau and previous advisory inputs, which there are 45 different discrete combinations of those. So we split the table up into 45 small subtables and trained a neural network on each one of these smaller tables. And because each of these networks is representing a smaller amount of data, we can make the neural network smaller and maintain that same level of accuracy. But at runtime, you're only going to be evaluating one of these neural networks for every point. And so because these neural networks are smaller, we're going to be able to get a faster runtime. So in this final version of the ACAS Xu prototype neural networks, we had 45 neural networks, which had 270 ReLU activations each, and still a total of 600,000 parameters. So that's in total 2.4 megabytes to represent all 45 of these neural networks. So next we wanted to compute the performance of these neural networks in comparison to the original table. And so we did this in simulation on a set of 10 million encounters. And using these simulations, we computed 4 different probability metrics. And for each one of these metrics, we would like to minimize them. So these are the probability of a near-midair collision, the probability of giving an alert, the probability of reversing the advisory direction, and the probability of splitting turning advisories with these clear of conflict advisories. And so what we found is that the neural network actually gives fewer alerts and is slightly safer. So it's giving a lower probability of NMAC and a lower probability of alert, which is very exciting because it means that it's able to outperform even the score table that it was trained to represent. There is a slight increase to the probability of reversal, but as overall, it's a pretty good match and seems to perform just as well as the original table. However, it is 1,000 times smaller than the original score table. And in runtime, it performs just as well as the nearest neighbor interpolation. So this is a really exciting result because 2.4 megabytes is much smaller than 2.4 gigabytes, and it's something that could be used on hardware that has limited memory available. And I wanted to briefly mention that we used the same approach to create a 5 kilobyte neural network that directs an unmanned aircraft to waypoints. So this is kind of the opposite of collision avoidance. It's directing the aircraft to reach a certain point and arrive there with a given heading angle. So this 5 kilobytes is small enough that we can actually put this on a 3DR Pixhawk, which is a hobbyist avionics system, and fly this on a custom-made unmanned aircraft to have it autonomously navigate this race course, which was parameterized by 12 different waypoints. And so the flight test results show that the neural network was very effective and was able to guide the aircraft along the race course just as well as we would have expected in simulation. So we're able to take these optimized solutions from the Markov decision process framework that might have hundreds of megabytes or many gigabytes and compress them to really small representations so that we can deploy them in real systems with limited hardware, but still maintain that same level of accuracy. So to summarize this contribution, we've shown that neural networks can efficiently represent a large amount of data, and that an asymmetric loss function is really important when trying to learn a representation for both the score values as well as the policy. And through simulation and flight tests, we were able to show that the neural network can perform as well as the original table, but it requires significantly less memory. So as a result, we can take these optimized solutions and deploy them in systems with limited memory, limited hardware, and get the benefits of that optimization deployed in real systems. However, there are some limitations to this kinds of approach, in that these neural networks are difficult to verify. So if it's a safety critical system, which is often the case with controllers for aircraft, we want to make sure that we can verify that it's going to be safe. And so this brings me to my next contribution on neural network verification. So the worry with neural networks is that we will only test and plot some finite number of points. So in this case here, this is a policy plot in which this region here seems to be continuous, strong left, which is what we would expect, because if the intruder aircraft is to the own ship's right, we would want to give a strong left advisory. But we're actually only plotting some finite number of points, some finite number of pixels. So if we were to zoom in, it's possible that there is some counterexample where there's a different advisory, maybe a strong right advisory, which could be really dangerous. So we might have just missed this point in testing, we might have missed it in plotting. And so there's no guarantee that these adversarial examples don't exist, and that eventually at some point we will run into them and have a catastrophic failure when there should be no such failure. So these kinds of problems can be addressed by neural network verification tools, and I've been a part of the teams to develop Reluplex and Marabou. So the idea is that we look over some small region of the state space and analyze the network weights and parameters in order to analyze the outputs of the neural network and search for a counterexample. So in this case, we might hope that this output region is all that strong left, it's all green, but we will be searching and looking for some point in this region where the advisory would be different. However, if we can't find such a counterexample, then these tools provide a guarantee that none exists. So this is a really powerful proof and can be used to help verify these systems. So with Reluplex, we were able to create some of these input-output properties using the ACAS Xu prototype neural networks that I generated. So these properties take the form that in this region of the state space, this is where the intruder is to the left of the own ship, we should give a strong right advisory. And likewise, if they're to the own ship's right, we would want to give a left turn advisory. So these just make some intuitive sense, and by plotting the policy, they appear to hold, but with using neural network verification tools, we can guarantee that they hold. So this is really exciting, And the properties like these have become a standard benchmark in the neural network verification field, in which all these different tools are using this kind of benchmark to showcase how quickly they can verify properties like these. However, these properties alone do not guarantee safety, because there is no notion of how these properties relate to multi-step safety. We need to incorporate the system dynamics to show that we are not going to reach unsafe states. And safe in this case, I mean specifically to avoid near midair collisions, which are avoided if we have at least 100 feet vertical separation or 500 feet horizontal separation. To study multi-step safety, I created the VerticalCAS collision avoidance system, which is a notional vertical rate collision avoidance system inspired by the ACAS XA system, but it's just a really simple way to define the Markov decision process framework and create a neural network representation. But the idea is that if we can improve safety for a simple system like this, then we would be able to verify and improve some safety with real systems like ACAS X. So we use that same Markov decision process framework in which we define the state space. In this case, we have 5 state variables. There's the relative altitude, h, the climb rates of the own ship and the intruder aircraft, and the 4th variable, tau, which in this case is a time to loss of horizontal separation. So very similar to the tau for horizontal collision avoidance systems, it acts as a countdown, in this case until we need to be separated vertically in order to avoid a near midair collision. And again, we have the previous advisory as the last state variable. We have 9 vertical rate advisories, which are the actions. These are different combinations of climb at different vertical rates, as well as that same clear of conflict that we had before. We have a dynamical model for how these state variables change with respect to acceleration terms for the intruder aircraft and for the own ship. And so these are governed by the intruder model and by the model for how the pilots are going to respond to our advisories that we give them. And we were able to use that dynamic programming to compute a score table, which in this case has 1.2 gigabytes of memory. And this is showing a plot of the policy. So this is now a side view of the system, in which we have h on the y-axis and tau on the x-axis. And so what we're showing is the policy that the table would give if the intruder aircraft were at these different locations. So if they're far away or well below or above the own ship, we'd issue clear of conflict. And if they're above us, we would say descend. And if they're below, we would say climb. And so we can train a neural network representation. In this case, it only has 104 kilobytes for the memory. And so it's a much smaller representation. And just visually, it seems to perform pretty well. And it's a decent approximation of the policy. So we could create some intuitive properties for this VerticalCAS system, just like we did for the ACAS Xu prototype neural networks. So for example, we could say that in this region, if the intruder is above us, we should descend, and if they're below us, we should climb. However, we don't really know how to define properties that get near this boundary. We can see that there is some curvature to this line, and it's not clear if this curvature is going to compromise safety. You know, if this had some more variation to it, would that lead to unsafe situations? And so that brings us to this bounded dynamical modeling, in which we can create more accurate safety properties than just these simple ones. So by this bounded dynamical model, I mean that we look at the system dynamics and we need to place some constraints on these acceleration terms. And so we would say that for each advisory, we have a minimum and maximum acceleration value that the pilot will respond with in order to comply with the vertical rate advisory. And we would have some constraints for the intruders' accelerations as well. And so later on, we'll talk about how we can relax some of these constraints and get different results in their proofs. But we have to assume some hard limits on these accelerations in order to get hard limits on the states of the system that we could reach at the next time step. The idea is that we can use this bounded dynamical model in order to create these safety properties that we can verify with tools like Reluplex. So the end result of this analysis with the bounded dynamics is these safeable regions. So these safeable regions can tell us regions of the state space where an advisory is unsafe, but a safe advisory does exist. So for this cyan region, it would tell us that we should have no climb 1500 And if we were to issue descend 1500, we would be safe. So we can check this with Reluplex and show that indeed climb 1500 is not given within this cyan region. However, there's also regions like the lime region, which says that nowhere within here should descend 1500 be given. However, we see that there is a small little spot where descend 1500 is given within this lime region. Actually, the only way for these properties to be satisfied, for both of them to be satisfied, is if the alerting region for the neural network passes exactly through this point. Otherwise, there's going to be a counterexample in either one of these regions. So this property is unlikely to ever be satisfied, but it can help us inform the neural network to try to improve its accuracy so that it can get as close to this point as possible. And I should mention that it's not just this one point, this is an example, but there's going to be points like this throughout the state space. So it's a bit unrealistic to try to meet this kind of specification. However, we still have hope at proving safety using the neural network. If the system gives advisories climb or descend earlier than this point, then we might be able to avoid this critical point altogether. And so that's the idea behind reachability analysis. So in reachability analysis, we first start by discretizing the state space into a number of discrete cells. And so let's consider this cell in particular. So we're going to use ReLU, which is another neural network verification tool, to compute the advisories that the system could give within the cell. So in this case, it might be climb 1500 or descend 1500. So we'd say that we can over-approximate the policy by making the assumption that the neural network could give either of those advisories from any point within the cell. So next we take a look at that bounded dynamical model in order to compute the region of the state space that could be reached at the next time step. So let's say that we begin in this small black region here. Using the system dynamics, we can take some samples, and these are some samples of the states we could reach at the next time step. But because we know a mathematical model for this dynamics, we can compute some bounds on these points. And when necessary, we can over-approximate the dynamics if they're nonlinear. So next we compute the cells that overlap with this red region. And we make the further over-approximation assumption that if we begin within this black cell, we could end up in any one of these cyan cells at the next time step. So if we do this approach for climb 1500, we could end up in either one of these cells. And then if we consider descend 1500 advisory, we could end up in any one of these cells. So we can repeat the process for all the cells that we could end up in until finally we reach tau equals 0 seconds, or time to loss of horizontal separation is 0 seconds. And at this case, we see that there are no cells that are reachable within that 100 feet of vertical separation, which means that by the time that we've lost horizontal separation, we have gained vertical separation, and so we're going to be safe. The idea is that if this over-approximated system can't reach an unsafe state, then the real system is going to be safe too. We can read this analysis not just for that one initial cell, but for a whole set of initial cells. And the analysis works the same way, where we compute the reachable set until finally we reach the time to loss of horizontal separation is 0 seconds, and show that we have no cells reachable within 100 feet. So we've gained vertical separation. So what are the initial set of cells that we should use for VerticalCAS? So we can either be separated initially horizontally, and this is to say that tau equals 40 seconds, but we could have any relative altitude or climb rates of the own ship or climb rates of the intruder. So in these plots, I'm showing 2 of the state variables, and the other state variables I'm just going to show by this color to show where states are reachable. And so for tau equals 40 seconds, all possible relative altitude and climb rates are reachable, and so we have every state as being reachable. However, we could also be separated initially vertically, which can happen for any tau value, but it means that we need to have the extreme altitude. So we have a band for the intruder could be well above us or well below us, but we could have any initial climb rate. The intruder could be at any climb rate, and so we have these yellow bands here. And so this red band here is the NMAC region. So we are going to have an NMAC if we have any reachable cells within this band by the time tau, or time to loss of horizontal separation, reaches 0 seconds. So now that we've established our initial set, we can do the reachability analysis. So in this reachability analysis, we start at the maximum time to loss of horizontal separation, and we count down the time until we've lost horizontal separation. And at that point, we hope to show that there are no reachable cells that are within this near midair collision band. And at each time step, we're going to make sure that we include in the reachable set these extreme altitude values. So that's saying that the intruder aircraft could appear either above us or below us at a horizontal distance that's less than 40 seconds. So in total, there are 109 million cells, which required 8.8 billion ReLU queries, and in total took 254 CPU hours. However, each of these ReLU queries can be run independently of the others, and so if you have a lot of CPUs, you can greatly reduce the wall clock time it takes to do this reachability analysis. And so now I'm going to show the reachability analysis in this video on the right to show how the reachable sets propagate over time. So at this point, we have almost lost horizontal separation, and we can see that we have a lot of cells that are unreachable, especially at these relatively low altitudes. So we still have some reachable states within this near midair collision band, but these are states where the own ship is descending quickly in order to pass below the intruder aircraft, or climbing quickly in order to pass above the intruder aircraft. And by the time that we've lost horizontal separation, we've gained vertical separation. And we can look and see in this plot that we can have at least about 400 to 500 feet of vertical separation at the time that we've lost horizontal separation. We all don't know when we're going to regain horizontal separation. So to make sure that we're going to be safe, we need to ensure that the system maintains vertical separation for all time in the future. This can be done by continuing the reachability analysis until we've either reached a near midair collision or we have reached a steady state set, so that we can inductively show that we're not going to have any near midair collisions in the future. So we can continue this analysis and we'll see that we reach a steady state without any near midair collisions. The results that we get from reachability analysis depend on the dynamic constraints that we've placed on the aircraft. So in the results I just showed, I had assumed exact accelerations for the own ship's response and for the intruder aircraft. So I can start to relax some of these constraints by using these delta terms, which allow us to expand the allowed acceleration ranges for the own ships in response to the advisories, as well as for the intruder aircraft, which is just accelerating on its own. So with these nominal accelerations, we will have large safety margins. As we start to increase those delta values, and now we have a wider range of accelerations possible for the own ship aircraft as well as for the intruder aircraft, we begin to see that some unsafe states can be reached by this over-approximated neural network controller. And so as we relax these constraints on the accelerations, the aircraft might start responding sluggishly, or the intruder aircraft might just accelerate at the worst possible time, and so the system could be unsafe. So just because an unsafe state is reachable with this analysis doesn't mean that the neural network is going to be unsafe. It could be just due to the over-approximation errors that we're able to reach these unsafe states, but we're just not able to make a claim when we have reached unsafe states with this analysis. But we do wonder, is this the result of the neural network making errors that have accumulated and are now showing, or is this a limitation of the original table which it was trained to represent? So to check this, we ran the same reachability analysis with all the over-approximations using the table and compare that to the results with the neural network. And what we found is that in all places where the table can be shown to be safe, the neural network is also safe. So the fact that the neural network was having, with some dynamical models, is able to reach unsafe states is not caused by the neural network making compromising errors. It's more so due to that the table is also not able to be safe, and that maybe these over-approximations have accumulated so that we can't verify safety for some of these more relaxed dynamical models. So we did the same approach for a horizontal collision avoidance system. So this is again similar to VerticalCAS. I created a horizontal collision avoidance system that is inspired by ACAS Xu. It's just a really simple system, but has similar state space and action space. And we did the same reachability analysis. And in this plot, we're showing a top-down view of the reachable states. And so this NMAC region is this red dot in the center. And so initially our tau value is 80 seconds, so its time to co-altitude is 80 seconds. And this took 14.8 billion ReLU val queries, but everything else is a very similar process. And I won't show the video, but by the time we reached co-altitude, we have gained horizontal separation around this unsafe NMAC region. So it's the same idea, is that we can assume some bounded dynamical models for the horizontal dynamics as well. And we were successful in showing that the horizontal collision avoidance system can be safe when using a neural network controller. So to summarize this contribution, verification is really important for safety critical neural networks. We used the system dynamics to create safety properties, but we found that those safety properties are too strict to be satisfied in order to guarantee safety. So to overcome those limitations, we presented a reachability method that can determine if unsafe states can be reached by the neural network. And we demonstrated this approach using both horizontal and vertical collision avoidance systems. And we could show that for some bounded dynamical models, the neural network can be safe. We made comparisons to the table to show that anywhere that the table could be proven safe with the same analysis, the neural network could also be proven safe. However, the verification methods I just described have a couple of important limitations. So with the reachability analysis, we had to discretize the state space into a large number of cells. And that number of cells is going to grow exponentially with the dimensionality of our state space. So if our input is high dimensional, such as with an image, then those methods are not going to be tractable. In addition, we needed to assume a bounded dynamical model for how the states are going to change in response to the actions. But when our input is an image in the real world, it's very hard to define exactly how these pixels are going to change in response to the actions we take. And so in order to overcome these limitations, this third contribution is going to be talking about how we can validate neural network controllers instead of verify them. So in this work, I'll be considering the aircraft taxi problem, which tries to use images from an onboard camera to steer an aircraft along a runway. So this is done in the X-Plane 11 flight simulator. And so we have some camera views from a simulated camera on the aircraft that we want to try to use in order to steer the aircraft to fly along this runway. So I created a neural network controller that takes in downsampled images coming from the camera and trains a neural network through supervised learning to predict the cross-track error and the heading error. So that's the lateral position of the aircraft on the runway, as well as the direction that the aircraft is heading in with respect to the direction of the runway. So I manually created a control law that combines these two predictions from the neural network into a rudder command that we use to steer the aircraft, and that is used within the X-Plane 11 flight simulator to control the aircraft for 1 second, and then we repeat this process. And so we simulated the aircraft in both clear conditions and in overcast conditions, and the simulations perform well. So from any initial starting point of the aircraft on this runway, whether it's cloudy or clear, we were able to get a neural network that is accurate in controlling and steering the aircraft towards the center of this taxiway. But the question is, with a lot of these image-based neural networks, is the neural network robust to image noise? So this is typical for image-based neural networks, but I'm taking it one step further to say, can image noise cause us to leave the taxiway? So we're going to incorporate the system dynamics, or in this case, we're going to use the X-Plane 11 as this black box simulator in order to search for image perturbations that can cause us to leave this taxiway. So to do this analysis, we brought in the neural network verification tool Marabou within the control loop. So we would receive some input image X and propagate that through the network in order to compute the rudder control. We're going to use Marabou to search in the neighborhood around this example image such that the perturbation is bounded by some value delta. So this is a different delta than what I previously mentioned, but it's going to constrain the amount that we can perturb this nominal image. And we want to search for the largest epsilon1 or the smallest epsilon2. So this is asking how much can we change the rudder controller by just adding noise to this input image to the neural network. And we can use Marabou to find the exact worst case image that is going to change the output of the controller as much as possible. So now I'll show a simulation that uses Marabou to compute the worst case left disturbance at a delta level of 3%. So we're allowing Marabou to change this downsampled image, these pixels, by as much as 3%, and find the image, the perturbed image that's shown on the bottom right, such that we push the aircraft to the left as much as possible. So in this simulation, it pauses for a few seconds to allow Marabou to compute that worst case image. So it takes a few seconds each time that we call Marabou, and the aircraft begins to head towards the left. And we'll just speed up this video. But what we find is that we don't reach the edge of the taxiway. We actually only reach about 7 meters or 7.5 meters of cross-track air. So just going left at each time step is not enough to push us off the runway. And we can repeat this process for right sense disturbances, and we would get the same result. However, we haven't considered all combinations of left and then right sense advisories, which brings us to adaptive stress testing. So in adaptive stress testing, we're using reinforcement learning combined with this neural network verification of Marabou in order to compute sequences of input perturbations that are the most likely to lead us to failure, or that do lead us to a failure. And so we consider the X-Plane 11 as a black box simulator. We don't need to know anything about the aircraft dynamics or how it creates the images. We use Marabou to take in the image that we get and compute the worst case left or right sense disturbances for that given delta level. And then we have a reward model that rewards this system for finding or getting near failure states. So in this case, that means leaving the taxiway. And so there's a lot of different reinforcement learning algorithms that we could use, but we used Monte Carlo tree search. But in my work, I've also used deep Q networks. And so now I'll explain how the AST can be applied to the aircraft taxi problem. So we begin with our root node at some state of the aircraft where we're near the center line and heading in the direction of the taxiway. We do this Monte Carlo tree search, which is sampling these different kinds of disturbances and using the simulator to propagate to see which state we can end up at the next time step. So we build this tree, the search tree. And what I'm showing here is these red nodes are the different states that we can reach at different time steps. And this blue path represents what Monte Carlo tree search thinks is the best value. It's the policy that it thinks is most likely to lead us off the taxiway. So we can continue this process, and we'll notice first that it has the same problem, that just going left at each time step, we don't leave the taxiway. However, we also notice that Monte Carlo tree search chooses to expand the tree more deeply in areas that seem more promising, which is the areas that are closer to the boundaries of the taxiway. But areas of the state space that are close to the center line, it doesn't explore as deeply, though it does give some consideration to them. So Monte Carlo tree search has this nice way of balancing that classic exploration versus exploitation problem. So we can continue the analysis until finally Monte Carlo tree search does find the failure, and it finds it in an interesting way. So it was able to find it by first going left and then swinging back to the right. So kind of like a pendulum, it's able to gain momentum and then eventually leave the taxiway off the right edge, even though it went to the left first. So the results that we get from adaptive stress testing depend heavily upon the delta that we choose. So what I had shown was a delta of 3%. If we had chosen a smaller delta value of 2%, we are not able to find any sequences of image disturbances that lead us off the taxiway. So this is not a verification that such a sequence doesn't exist, but it is strong proof that we would likely be safe with this kind of disturbance level. On the other hand, if we had really strong disturbances like delta of 4%, it's very easy to find sequences that lead us off the taxiway. We can head straight to the left and we'll leave the taxiway. What's interesting though is adaptive stress testing is able to find interesting ways in which the system can fail by going left and then right, or right and left. And so let's take a little bit closer look at this delta of 3.5%. So now I'll play a video that walks us through the adaptive stress testing solution at delta of 3.5%. So I've shown the tree here just to remind us of what that search tree looked like. And we're going to walk through this blue solution that it found, just to take a look as to how it's able to leave the taxiway using this solution. And I want to draw particular attention to this rudder error term here, where a negative number means that Marabou is confusing the neural network to push the aircraft more towards the right, and a positive number means it's pushing the aircraft more towards the left. And the greater the magnitude, the stronger the push is going to be. So as we play this video, Marabou is pausing every few seconds in order to compute the perturbation. This value is typically around 0.1 or less. And so that's kind of weak perturbations, but eventually the adaptive stress testing pushes the aircraft towards the center line, and actually this number begins to spike. So now we have values at around 0.2. This is a really strong perturbation, and if we take a look at this downsampled image, we have some clues as to why. This center line is during a gap, so there's not a lot of features in here to tell the neural network where it is on the taxiway. And as a result, it's easy to perturb this image and fool the network into thinking it's in a different location or at a different heading direction. And so adaptive stress testing is explicitly exploiting this weakness in the neural network and this vulnerability and putting it in this situation because it's able to have strong rudder commands that are going to gather a lot of heading error such that the aircraft has no choice but to leave the edge of the taxiway off to the left. So if we continue this video, we'll see that again, the rudder error is high, and as the center line comes into view, it decreases, but now we've gained such high heading error that there's really no hope, and we begin to reach an area of the state space that is outside the region where we have trained the neural network, and so this rudder error becomes really large. So we can also try adaptive stress testing with more actions. The idea is that we can find sequences that have different levels of disturbances within one sequence. So we don't have to just have one delta level for the entire search tree. We can have a mixed search tree. And we can do this by just incorporating more actions. So for 4 actions, we could have left and right disturbances at 2 different delta levels, 6 actions, 3 different delta levels, and so on. What we found is that increasing the number of actions results in sequences that take longer to reach a failure, but the average disturbance to the input image is lower. So these are sequences that are more likely than these strong perturbations. So it's able to incorporate some of these softer perturbations to the input images and only use the stronger perturbations when necessary and still reach a failure. So just to summarize this contribution, I presented a method to validate neural network controllers. And this is really useful for image-based neural networks when the verification methods are not very feasible. We use local robustness verification combined with reinforcement learning in order to search for sequences of input perturbations that cause the system to fail. So we demonstrated this algorithm with a tiny neural network for autonomous aircraft taxiing, and we're able to find perturbations that lead to failure. And when we took a deeper look into the failure modes, we discovered a vulnerability of the taxi network, which we can then use if we were wanting to implement this in order to try to make the network more robust in those kinds of areas, or maybe change the downsampling mechanism to try to give the network more information during the centerline gap. So to summarize my contributions, we first discussed a method for training a neural network to compress tabular policies and show that even though the neural network is 1,000 times or more smaller than the original table it was trained to represent, it can still be shown through simulation and flight tests to perform just as well as the original optimized table. We then talked about a couple different methods to verify these neural network controllers by looking at models of the dynamics we briefly mentioned the results from this dynamics-informed safety properties, which led us to the idea of safeable regions that we can verify with neural network verification tools like Reluplex. And then we also talked about the verification of neural network controllers through reachability analysis, which is able to show that an over-approximated neural network system is unable to reach unsafe states, and so the real system will also be safe. And then we address some of the limitations of these verification methods by looking at validation of neural network controllers by combining adaptive stress testing with neural network verification tools in order to find sequences of input disturbances that cause failure. So there's a lot of room for future work. For one, we could look at methods to improve the reachability analysis. If we can reduce the over-approximation errors, then we can get better guarantees and guarantees of safety that are more realistic for what aircraft might actually behave like. We can also take a look at probabilistic reachability. And so the idea would be if we had a distribution that is more realistic to how pilots will actually respond to advisories, we can try to model with what probability certain states are reachable, and it might give us a better estimate of how real systems are going to be safe. We can also take a look at verification of neural networks with continuous actions. So far I've pretty much focused on discrete actions, but these methods can also be extended to consider continuous action spaces. I think it would also be interesting to look at autoencoders in order to reduce image dimensionality. And if we can reduce that image dimensionality and come up with a model for how these codes change in response to the actions that we take, we might be able to apply some of these verification methods even to image-based problems, which would be really interesting. And there's lots of room to do real-world testing. And this is really important for image-based networks because there's always the question that if we train and test these networks in simulation, how is that going to translate when we bring them into the real world? And there's lots of questions to be asked and addressed there, and lots of room for future work there. And here are my publications. So the ones that I've highlighted are the ones that I've talked about in some detail in this presentation. So that's all I have. So thank you for taking the time to watch this, and I hope it was interesting and informative.